Recording started.
Okay, good evening, everybody. Professor Ayorinde welcoming you to another organic chemistry session. In case you forgot my name over the weekend, right? Anyway, so today we do have a lot of material to cover today. But before we get started, I do have a few announcements to make. Tomorrow, 7 p.m. tomorrow, that is Wednesday, January 25, there will be an online review session. And for that review session, we are going to use the end of chapter questions in chapter 16, that's chapter 16 in OWL. That is 7 p.m. tomorrow, Wednesday. Also on Monday, January 30, there will be another online review session. This time we'll be reviewing for the first exam that is scheduled for Tuesday. The material that we are going to use for that review will be the previous first exam that was given in spring 2011. By the way, I already posted that material in Blackboard, just in case you might want to take a look at the that exam. Yes, do you have somebody has a question? Yes. The Monday review session will be 7 p.m. Okay. I will send you a reminder for tomorrow's review and also for Monday's review. I will send you an email reminder for each one of those. But just in case you do not get my email, you should go ahead and use the link that we used for the review session of last week. Also, the homework assignment for this week has been posted in Blackboard, and that is the OWL end of chapter questions of chapter 16, that is chapter 16, and that is due on Sunday, January 29 at 11 p.m. Due Sunday, January 29 at 11 p.m. And finally, of course, you know that the first exam is scheduled for Tuesday, that is January 31st. Okay, so let us get going here. We do have a lot of material to cover. If you recall, when we left on Thursday, we were discussing electrophilic aromatic substitution reactions. Electrophilic aromatic substitution reactions. But before we come to the item on this particular slide, what I want us to do is to do a little review of some of the reactions that we discussed on Thursday. Okay, so let us do this together now. Supposing I give you this. I give you the benzene molecule, and I give you this reagent here. Does anybody know the product of this reaction? Yes, very good, excellent. Nitration, Tony, you said nitration? Okay, very good. So that would be nitration, so that means the product will be nitrobenzene. Excellent. So I think you guys are getting ready for the exam. So that would be the product, okay? In this case, of course, what we are doing here, we are replacing this hydrogen here with the nitro group. And that is why we refer to this as electrophilic aromatic substitution reaction. Now supposing I take the same benzene molecule and I give you this reagent, what will be the product? Chlorination. Excellent. Chlorination. So here we will get chlorobenzene, right? Very good. Now supposing take the same benzene and I use this reagent here, sulfur trioxide in the presence of sulfuric acid. What is the product? Somebody said? Okay, Jessica said benzene sulfuric acid. Excellent, good. So here we get benzene sulfonic acid, in which the sulfonic acid group, this group here, are substituted for the hydrogen atom. Okay. Now, supposing we want to do a reaction, electrophilic aromatic substitution reaction, in which you have a substituent on the benzene molecule. The question now is, what is the effect of the presence of the substituent on that benzene molecule? For example, here there is a result of experimental result from an experiment in which you have a series of substituted benzene molecules have been reacted with nitric acid in the presence of sulfuric acid. What reaction is that? Nitration. In other words, there is nitration going on here. In this particular experiment, this Y here, this Y represents, in this case, could be nitro group. It could be the chlorine atom. Of course, in the case of benzene, it will be hydrogen. And here, in the case of this phenol, this hydroxy group. That is what this Y represents. So now we perform nitration on this series of compounds, and you begin to see the results. Here, the rate of this reaction here, when the hydroxy group is on the benzene ring, is 1,000 times faster than the rate of the reaction with benzene itself. So what conclusion do you think we will make regarding the effect of the hydroxy group on electrophilic substitution reaction? What kind of effect do you think this will be? What is it? Is it catalytic? Okay, catalytic. Okay, fine. That's great. Yes. Any more? You are in the right direction. Tikia, go ahead.
I would say either the more electrophilic or nucleophilic reaction.
Excellent, excellent. In other words, the effect of the hydroxy group is to activate the benzene ring. So we say this is an activator. So we say the hydroxy group is an activator. Now let us take a look at the nitro group on the other side of the spectrum. If you look at the nitro group, look at the rate of the reaction compared to benzene molecule. It's almost millions times less reactive than the benzene molecule. So what are you going to say about the nitro group with respect to the effect on electrophilic substitution reaction? The activator, is that David? Yes, excellent. So therefore, we say here, we say the nitro group is a deactivator. Okay, very good. So on one hand, we have an activator, which is hydroxy group. On the other hand, we have a deactivator, which is the nitro group. But somewhere in between, we have the chlorine atom. Look at the rate of the reaction with the chlorobenzene compared to benzene. What would you say this is? It's slow. Is it slower than in benzene? Exactly. So, but it's not that much, it's not as great as in the case of the nitro. So therefore, I will refer to the chlorine atom as a moderate deactivator. Okay? Let us call this moderate deactivator. So now, we have three types of effects in terms of activation of the benzene ring. We have the activator, the deactivator, and moderately deactivator. Now, what will be the implication of this? Okay, Tikia, go ahead.
The benzene is a moderate activator.
Yeah, the benzene, the benzene is the reference. Okay, we at this point we are using benzene as our reference. So the chlorobenzene is a moderate deactivator. Okay. So anyway, what is the implication? Now, if we go to the next slide, begin to see the implication of this. On this slide, we show you all of those groups that are deactivators. The nitro group is a deactivator. The sulfonic acid group, deactivator. The carboxyl group, deactivator. All of these groups on this slide are deactivators. Now we see something else. All of those deactivators, when they are present on the benzene ring, they direct an incoming group to the meta position. So we call them meta directors. Now, what do we mean by this? What this means is, if, for example, I have they direct an incoming group to the meta position. Okay. Now, what do we mean by that? So, for example, if I have nitrobenzene, which is a deactivator, and then I want to perform bromination, right? Now, based on what I just told you, what do you think the product of this reaction will be? What is it? Nitration. But what is the position that bromination? What position will the bromine atom go to? Where? Will it go to the auto position? Exactly, meta position. So this is a regio-specific reaction. In other words, the product you are going to obtain will be this product here. You see, because the nitro group is a meta director. So whenever you perform electrophilic aromatic substitution reaction involving any one of the deactivators, the incoming group will go to the meta position. Yes.
So all the ones on that slide are meta directors?
They are all meta directors. So you need to know this.
But the carboxyl group and the are those?
Yes.
Are those still deactivators, or is it?
They are all deactivators. All of these are deactivators. All of the deactivators are meta directors. Okay? So here, we have this here. For example, if you have the question that Emma is asking, okay, is the carboxyl group a metal director? Yes. So if we perform the same reaction, bromination with iron 3 bromide as a catalyst, what do you expect the product to be? The metal bromo what? Benzoic acid, right? Exactly. So the product would be metal bromo benzoic acid. Okay, is that clear so far? Okay, so therefore, all of these groups here, anytime you see them on the benzene ring and you need to perform electrophilic aromatic substitution reaction, the incoming group will go to the metal position. Now, if you go to the next slide, now we have the other side of the equation, in which you now have the activators. These are all activators. And of course, we have the moderate deactivators. On this side, the halogens. The halogens are moderate, what I refer to as moderate deactivators. So all of these groups here, the moderate deactivators, in this case the halogens, and all of these groups that we show you here, we refer to this as auto-para directors. These are auto and para directors. In other words, they would direct an incoming group to the auto and to the para position. What does that mean? If I have this, supposing I have this, say I have a methyl group, and I want to perform the same bromination that I just gave you. Bromine, iron 3 bromide. What will be the product? This time you are going to get two products. You will get two products. Exactly. So you are going to get one product, which is the auto bromo toluene. This is toluene right here. Plus you get the auto product, plus you get the para product. Exactly. I will tell you now, in terms of the which of these will be the major product. Generally, the para product is generally more of the major product because of steric hindrance. Okay, so you have this. Okay, so each one of these is an auto para director. Each one of these is an auto para director. Yes, take care. Yes, in the case of the auto para products, you need to show both of them. Okay, show both of them. Now, supposing you have a molecule that contains an auto para director, which is an activator, and a meta director, which is a deactivator. What group do you think will control the position of the incoming substituent? Which one? The activator, exactly. So, okay, the question is, supposing you have this. Supposing you have this. Okay. And you have this. Supposing you have that. Okay? And then I say, okay, we want to perform, let us use chlorination. Want to perform chlorination. The hydroxy group is an activator. Okay? It activates the benzene ring. The nitro group is a deactivator. So in this particular instance, the activator will take charge of this reaction, will direct the incoming group. Okay. So therefore, we expect the incoming group to go to where? To go to this position and to this position. Because the hydroxy group is an auto-para director. Okay. Yes, Emma, go ahead.
So activators always position, even if there's more deactivators in it, like there's multiple nitro groups put on the line.
So the activators are always taking charge. Yes. Even within the activator group, the greater the activation, the more the activator will take charge. I will show you what I mean by that. Just a minute. Okay, in this particular instance, you have this. Okay, so you have the chlorine here. Go to the auto position of hydroxy group plus the para position of the hydroxy group. Now, yes, David. Yeah, it doesn't matter because the hydroxy is directing to the para position anyway. It's just a coincidence that the nitro group is also there. Okay, yes. Now, the question that David was asking, does it matter that the nitro group is also metal director? I said that is just a coincidence at this point. Yeah, Bria, go ahead. It is what? Yes. Okay, now, supposing we have this. Let me erase this here. Okay, look at this table here. In this table here, the amino groups is a greater activator than the methoxy group. Okay, the amino group and the hydroxy group, they are almost equal in terms of their activation properties on the benzene ring. Okay, but based on what we have here, what this is telling us, the amino group is a better activator than the methoxy group. So if I have an amino group on the molecule and I have this methoxy group, the amino will take over. Okay, so the direction will be based on the amino group. Okay, so what this is also saying is that the methoxy group is a greater deactivator than the methyl group, indeed than all the alkyl group. Yes, go ahead, Meredith.
Are you going to give us a chart on the cell so we know which one's the position?
You're supposed to know this chart. Yes. Well, as you go along, I will show you how to find out which is meta and auto. It's fairly easy to know. Yes. Yes, Emma.
That group called with the carbonyl group with the NH. Yeah, what's that called?
Okay. This one is called the acet amino group. but you don't. This one is. Okay, or you could simply just call it amide group. Okay. Okay. So anyway, so what is saying is the hydroxy group is a greater activator than the phenyl group. This group here we call the phenyl group. The group in which all we've done is to remove one hydrogen, that becomes the phenyl group. Yes. What's your name? I can't hear it. Say it out loud, louder. Princess. Okay. Okay, go ahead. Okay, we will come back to that later. That's a very good question. The question is, what makes one substituent a better activator than the other? But we'll come back to that later, okay? Any other question? Okay.
So the activators too, so whichever one's the strongest one always.
Yeah, even with the deactivators, if we go back to the deactivators, if you look at these deactivators here, the question Emma is asking is, do we have the same relationship with the deactivators? One more deactivating than the other? Yes. In this case, what you have here, this group on this side, on the right side, right here, they are less deactivating than this group. So if I have this group on the benzene ring, and I have the nitro group on the benzene ring, this will take over the direction. In other words, this would deactivate the ring less than this would. Okay? And that is why we have this chart for you.
So the base position of the aldehyde group?
The aldehyde group is less deactivating.
So which one would be base position?
I mean the position of the incoming group? Yeah, it will be based on the aldehyde group, yes. In other words, if I have this, say if I have this here, if I have that, right? And then I also have this here, okay? And I give you this reagent. I say, give me the product of this reaction. Okay, what would be the product be, based on our discussion so far? Yes. You know that this will take care of the direction. In other words, the direction or the position of the incoming group would now be based on this here. So this is the meta director, of course. So that means this is going to be here. Okay. Okay? Yes. Okay, now let's give you some more examples. Yes. Say your name again. You gave it to me, but I think I forgot. Kia. Oh, Kia. Oh, Kia Bird? Yeah. Okay.
Did you also add the bromine to the third part?
Yes, the bromine could also come here. Yeah. Yeah. But that would be also a product to meta position line. Very good. Okay. So now you know the effect of a substituent effect as it relates to the reactivity of an electrophilic aromatic substitution reaction. Now let's give you a few examples. Okay, so if we have this, we have toluene reacting toluene with sulfur trioxide in the presence of sulfuric acid. What kind of reaction do we call this? Sulfonation. So that is sulfonation. Okay, you see, it goes to the para position and the auto position. Now, in this case, here we have chlorination on nitrotoluene. This is nitrotoluene. Okay, in this case, the position of the incoming group will be directed by which group? By which group? Which one? The methyl group, exactly. Very good. So you have here the chlorine is in the auto position right here, and this other chlorine is in the para position relative to the methyl group. Okay. Okay. Now another example. Here, what type of reaction are we doing here? What type of reaction is this? Nitration? Yes, very good. We are doing nitration, and the direction, yes.
If you have a case where you have some that's less activated than hydrogen, like a halogen, would be less, so would the hydrogen be the...
Oh no, the chlorine or the halogen would direct, yes. Don't forget the hydrogen is just there. We are replacing the hydrogen anyway. Okay, we use the hydrogen in that experiment just as a reference. Okay. Okay. Okay, so in this nitration reaction, what are we doing? We're doing nitration, so the hydroxy group will take over the direction, so it comes to the auto position. And because the para position is already occupied, now it simply goes to the auto position. Now in this, the second reaction here, see what you have here, we have the chlorotoluene, metachlorotoluene. The incoming group could go here, if you look at it, it could go here or here. But anytime you have this kind of relationship in which you have a substituent, two substituents matter to each other, in other 1-3 relationship to each other. This group here, this position here, you say is fairly hindered. Okay? Will be hindered. So the incoming group will prefer to go to here, right here. And that's what you see here. Okay. Of course, we also see the other product in which the chlorine goes to the para position relative to the methyl group. So you find that this is really very simple. All you need to know just a set of rules that will guide you. Now, somebody asked a question earlier. How do you know which will be auto para directors and which will be meta directors? We do know that the meta directors are generally the activators, right? And the auto para directors are generally activators or moderately deactivators. I'm sorry about that. Let me turn this off. Does he want to go? Okay. So the question was, yes, if you have a question.
So for the chlorination, I thought it was activating group that is going to go to the ortho and para.
Yes.
So is that chlorine?
No, it did go to the auto. Keep in mind that, okay, as if we are starting with this chlorine is here already. Okay, the chlorine that came in is this red chlorine. Okay, which is the auto position relative to the methyl group. Don't forget that. Then the next one, this is the para position relative to the methyl group. Don't forget that the alkyl groups are auto para directors. You see that? Okay. Everybody see that? Okay. Now the question is, how do we know which is which? Okay, so let us how do we know auto para-directors and meta-directors? Okay. Any group in which the atom attached to benzene contains non-bonding electron pair, for the most part, will be an auto para-director. Let me tell you what do I mean by that. If you have this, okay, look at that group, right? Okay, even let me make it a little bit more complicated than that. You don't like that? You like it simple? Okay, well, I'll make it very simple then. Supposing we have that. Based on what I just told you, keep in mind I said any group in which the atom that is attached to the benzene ring contains non-bonding pair of electrons, that group will be auto para-director. In this case, you have non-bonding pair of electron on oxygen, non-bonding pair of electron on oxygen. Okay, so therefore, this group here will be an auto para-director. Okay, will be an auto para-director. The same thing here. If you look at most of the auto para-directors that are activators, all of the auto para-directors, for the most part, they have the atom that is attached to the benzene ring, they have non-bonding pairs of electrons. Okay? If we have, let's take a look at the halogens. Look at the halogens. Non-bonding pair of electrons. Now, on the other hand, well, let us continue that trend. If you also have a group in which you have, say in the case of the phenyl group, this group here, what we call the phenyl group, is an auto para-director because you have conjugation with the ring system. If you have this double bond is conjugated with the ring system. Anytime you have a double bond that is conjugated with the ring system, the chances are that group will be an auto para-director. Okay, there is conjugation here. Conjugation. Okay. Anytime you have a group that has conjugation with double bond conjugated with the double bond of the benzene ring, conjugation with a ring or benzene ring, when we say conjugation, we mean that you have a double bond here, single bond and a double bond. So this double bond is conjugated with the double bond here. What that tells us is that if you have this, if I give you this, okay, what kind of director would that be? This group right here. It will be an activator and it will be also autopilot director, because this double bond is conjugated with the ring system. Okay? So that means anything else will be metal director except for the alkyl groups. Okay? For the alkyl group, the alkyl groups, okay, let us just, instead of using metal, the alkyl groups are the only that we know of, at least that you know of right now, the only autopilot directors that do not have non-bonding pair of electrons on the atom that is bonded to the ring system. Only the yes. Okay? Only the alkyl group. So this is autopilot director. So what that means is everything else is a metal director. So you have the alkyl groups, autopilot directors. Any other group in which you have the atom that is attached to the ring system contains non-bonding pair of electrons, you know those are autopilot directors. Then anything else will be a metal director. For example, if I have this, here, okay, you know that's going to be a metal director because this carbon here has no non-bonding pair of electrons. But the fundamental reason why all of this is the case, I think somebody asked that question, why is something autopilot director and the other metal director? Was it you who asked that question? Okay, let us now get to that answer. If you look at the benzene ring, we give two explanations. One, resonance. I'm sure you guys have heard of resonance before, right? You know, whenever we are in doubt, the organic chemistry always go back to resonance. So resonance, right? Two, what we call inductive effect. Inductive effect is the ability to pump electrons into a positively charged center. In other words, if you have a molecule, you have more electrons in one side of the molecule than the other, the ability to draw electrons from one part of the molecule to the other is what we refer to as inductive effect. Now let us see. Okay, yes, correct.
Nitro groups have lone pairs on them? Nitro groups?
Do they have?
Do they not have lone pairs?
Okay, no. This is nitro group. The question Emma is asking, doesn't a nitro group have non-bonding pair of electrons? No. Okay, you see here, this is what a nitro group looks like. That's a nitro group. Now, does it tell you something? So that's a good question because it leads us to exactly where I want to go. The positive charge here, what is it doing? Drawing electron away from the ring. And electrophilic aromatic substitution depends on electron being in the benzene ring. So if you have a species that is drawing electron away from the ring, it will slow down the reaction. Okay? So let us now go back to, okay, takes us exactly to the reaction mechanism. So far, remember I promised you, all we did was just simply gave you the reaction. We had this starting material, we gave you the reagent, this is the product. Now, how do this reaction take place? When you know how this reaction takes place, then you begin to understand why some groups are also para-director and some are meta-directors. Okay, if you have the benzene ring, think of the benzene ring as nothing but just a ball of electrons. It's rich in electrons. You have electrons moving all over around here. So now you have an electrophile. Think of this here. This E here, let us now represent some positively charged center. We call it electrophile. What happens? We draw electrons from the benzene ring to the electrophile. And you form this intermediate. Okay? You have the electrophile here. And you form this intermediate carbocation. Remember what we told you earlier. That benzene wants to maintain its aromaticity. In other words, it wants to remain aromatic. Okay? So it does not want to undergo addition reaction. So far, what have we done here? The electrophile is added to the benzene ring to form this intermediate carbocation. Once you do that, now you form this, we could draw resonance. See, all of these are resonance structures. Now what is going to happen? That some kind of base or nucleophile will come in, pull this hydrogen off to regenerate the benzene ring. And that's what you have here. So we are going to regenerate the benzene ring. This base is coming here, pulling off this hydrogen. So now you form this. So in essence, we have replaced the hydrogen. That's what we've done here. We have replaced the hydrogen. Okay. Now, so now we have replaced the hydrogen. Okay, so therefore we say this is electrophilic aromatic substitution reaction. So this is the classic mechanism for all of these reactions. And this electrophile could be anything. This electrophile could be anything. Okay, so now let us see. Supposing I have this. Supposing I have this. I want you to follow me very closely now. Supposing I have that, okay, and I want to do let's say, in this case, let us say I add somehow I have found a way to generate the electrophile, this carbocation, right? And remember when we did the Friedel-Crafts alkylation, we generated the carbocation. Okay, so we formed the electrophile. This is your E+. Now what happens? Electron comes here, attack this. And of course we know that we have, see here, just because of this mechanism, let us show that we have this hydrogen here. Okay. So now, what do we form? We form this intermediate. If we form that intermediate, in which we now have hydrogen is here, Of course, the methoxy is here. We now have the materials here because the methoxy is an auto para director. Okay, so where will be your positive charge? Right here. Okay. Now let us write the resonance for this. Okay, if I write resonance for this, I move this electron to here. Where would the positive charge go? Go to this carbon. Very good. And the hydrogen is here, and the electrophile that we added, which is the methyl group, is here. The positive charge is now here. Can we draw another resonance? Yes. What do we do? Move this to here. Very good. So we move this to here. So now that goes to here. Now we have the double bond here. Now we have this here. And this hydrogen is here. And the electrophile, which is the methyl group, is here. Okay? Can we draw another? Oh, sorry, there's a positive charge here. Can we draw another resonance? Can we do another resonance? Yes, we could. Look at the non-bonding electron on oxygen. We could draw a resonance to... Yes. Okay? It's a resonance structure. So this one of the pair of electron comes here. So you now form double bond here. So this is still here. That means oxygen now has the positive charge. Okay? Somebody ask a question? Okay. So now we see I have this here. Let's see. This is still here. And this is still here. And this hydrogen is here. This here is here. Okay, now the point to be made here is when the electrophile goes to the auto position or the para position, you could draw 4 resonance structures. Now each resonance structure you are able to draw, the more stable the intermediate will be, and the faster the reaction will go. Okay? Keep in mind, resonance stabilizes an ion. So what we are saying here, when you have an auto-para director, the auto-para director stabilizes the intermediate carbocation. Okay? Stabilizes the intermediate carbocation. Because now, of course, we know that the product that we want could come very easily from here. Come from here, for example. If we have some kind of base, okay, comes in here, picks up this proton, Okay, and then that proton releases the 2 electrons to form to regenerate this here, and form your what I want you to do when you go home, do the same thing for this product. For the electrophile going to the para position, you will find that you will also be able to draw resonance contribution that involve this oxygen, because that's important. Now let us look at the case in which, supposing we assume that the incoming group goes to the metal position. Okay, let's do the same reaction. Okay, what we've done in that last series of mechanisms to show you why a group directs to the auto or para position. Now, supposing we say, now this doesn't happen. Supposing we say that for that same reaction, that electrophile, in this case the methyl carbocation, goes to here. Okay? It goes to the metal position. Okay? Let us see what happens. If it goes in the metal position, of course you have hydrogen here. This is here. So that means, okay, we move this electron to go here. The positive charge is here. So that means this is here. Okay? Can anybody tell me how many resonance structures I will be able to get here? I will tell you now, it's only going to be 3. Because no matter what you do, you will not be able to write resonance that involves the oxygen. Okay? Therefore, any group going to the metal position will not be as stable, intermediate, as when it goes to the auto and the para position. So let us move this around. Move this electron to here, right? We have that. If we move this to here, of course that will now go to here. Positive charge is here. This is still here. And this metal is here. Okay? We will draw one more. Notice here, no matter how we move those electrons within the ring, it would not involve this carbon here. And as long as you do not have a carbocation on this carbon, you cannot involve the oxygen. Okay? Okay, so we move this again. We draw another resonance. Okay, so we move this to here. So that is now here, and this one is still here, and of course we still have the metal here, and the hydrogen here. So you see, when it goes to the metal position, you do not get as much resonance stabilization. So that is why those groups in which you have non-bonded pair of electrons attached to the ring, they direct to the auto and para position. Now the question you want to ask me is, okay, how about the alkyl groups? The alkyl group do not have non-bonded pair of electrons. Okay, in the case of the alkyl group, if we could Okay, that keep in mind that the essence of all of this is that you must, for the auto-para directors, let's just say we have the alkyl group here. The intermediate carbocation must be on this carbon. That is why they direct auto and para. Okay? If it is here. Okay, so therefore we say that group is here. And this is here. Okay, that means we have this double bond here, this double bond here. Okay? You could draw some other resonance, the other resonance structure. It will be 3. But in the case of the alkyl group, because of the fact that carbon is more electronegative than hydrogen, it pulls electron from nitrogen. So this carbon is richer in electron, and as such it's able to also stabilize this carbocation. Okay, that is why the alkyl groups are auto-para directors, and that is what you call the inductive effect. So the reason why the alkyl groups are auto-para directors is because of the inductive effect. They do find a way to pump electrons to support the carbocation that is formed. Okay? Okay, I've been giving you this. Can you write the mechanism for why a group is meta-director now? Can I leave that for you? You should be able to do that, right? You want me to try one for you? Okay. Okay, now, why is a group, now so far we have given you why a group is auto-para directors. Because of resonance, contribution, or because of inductive effect. Now, why meta-director? Okay? Why meta-director? What time do we have? 15 minutes? Oh, we've got plenty of time. Okay. Plenty of, okay. Now we do this and then we do one problem before we leave. Okay, why meta-directors? Say we have this. Let us use the case of the nitro. By the way, we will continue most of this we will do during the session tomorrow, the online session tomorrow. So you have your nitro here. Okay? That is the nitro group. Now, so if we have a group, let's use our chlorination this time. Say that the chlorine is our electrophile, right? Because we could generate the electrophile that way. The chlorine is our electrophile. So, electron goes here, attach the electrophile. Now, this is a meta-director, so the chlorine will go to the meta position. Okay? By the way, I will try to post this this webcast for this lecture before I leave tonight. Okay, so if you do that, we have the chlorine goes to the meta position. So that means the positive charge will be here somewhere. And of course, this double bond is still here, and this double bond is still here. Now, let us draw resonance for this. Resonance. We move this electron. We move this electron to here. Okay, so if we move this to here, that means now we have this here. Now that means the positive charge is now on this carbon. Okay, keep in mind this double bond is still here, and of course this is still here. Okay, can we draw another resonance? Yes. Keep in mind our resonance cannot involve this carbon here, because this carbon is what? It's sp3 hybridized. Okay. Okay, so we draw another resonance. This time we move this electron, this pi electron to here, so the positive charge will now be on this carbon. Put this out of the way. Okay, if we do that, how we're doing, we now move this to, this is still here, this is here, and the positive charge is here. Okay, so we have those positive charge. Look at all of these resonance structures. At no time do you have the positive charge on the carbon attached to the nitrogen. You see that? See, all of these resonance that we've drawn here, for when the group goes to the metal position, at no time do you see the positive charge on this carbon. Do you see that? Now, suppose I allow the chlorine to go to the auto position. Okay? Let us assume that I allow the chlorine to go there to see what happens. Supposing, so this is what actually happens. Okay, of course, from here you have some kind of base comes in, pull this proton away from here, and then you form this.
So would that stabilize it even more and you have fewer resonance?
No, just a minute. I'll get there. Just a minute. Oh, you're almost there. You're almost correct. Okay, so you get your product. It will be now here, here, and here, in which now you have replaced the hydrogen. So this is where we remove the hydrogen because of the base is coming here. Now, let us, just for the sake of this argument, supposing the chlorine goes to the auto position. Supposing it goes to the auto position, which means that you now have chlorine here and the hydrogen here. So the positive charge will be, all of this will still be here. So the positive charge will be where? Right here. Okay, now let us draw resonance for this. Okay? If we move this to here, right? The positive charge will be here. Now you see why I delayed the mechanism to the end. Now if I started the mechanism at the beginning, you guys will have run out of here, right? I gave you the reaction first, and then we're now dealing with the mechanism. Okay. Okay, now we move this to here, so that means we now have the double bond is here, the positive charge is now here, and this is still here, and then you see I have this here, and this here. Okay, One more resonance. Okay? Okay, so if I now move this double bond to here, right? What will happen? The positive charge will be on this carbon, right? Okay? And now this will be here, and this will be here, and of course this is here, and this is here. See what has happened? This is not going to happen. This will not happen because what happens here, you now have a resonance contribution in which this positive charge, let me see, I cannot see my pen. This positive charge is next to positively charged nitrogen. That is destabilizing. And that is why those groups are meta-directors. In other words, they're choosing between two evils. Okay? Do I pick the meta-director or the auto-director? Of course, when they pick the meta-directors, the intermediate carbocation is not as destabilized as when they pick the auto-director. So that is why the meta-directors are meta-directors, because if they are auto-directors, the intermediate carbocation will be very unstable. You all follow that? Okay? So here we're using resonance to explain why we get the direction either in the meta position or the para position. Okay, now before we leave, let me just give you just a few more examples. We see two more about 5 more minutes, right? Oh wow, this is plenty of time here. 10 more minutes. 7:22 according to my time. Huh? Right? Okay. Is it 8? 7? Yeah. Right. Okay. Okay. Now a couple more examples. Okay, more examples of electrophilic reactions. Okay, so supposing we have this. What are we going to get here? We have not given you an example of this. Aluminum chloride in a chloroethane. What will be the product? What is it? Ethyl benzene. Okay, this is Friedel-Crafts. Remember Friedel-Crafts reaction. Friedel-Crafts. This is what we call Friedel-Crafts alkylation. Okay, so now we get this. Now the beauty of this reaction is we could now take this alkyl benzene. We could take alkyl benzene and react with potassium permanganate in acidic medium. We get see what we get benzoic acid. Now anytime you have an alkyl group, any kind of alkyl group attached to benzene, and you react that molecule with potassium permanganate in acidic medium, you are going to reduce or oxidize that alkyl group all the way to carboxyl group. Okay, no matter how big the alkyl group is. For example, supposing I have this. And I do this. What do you think the product will be? What do you think the product will be?
The substituent is the
Both of them. Both of them become carboxyl group. Both will become carboxyl group. Okay? It just opens up. In other words, anytime you have an alkyl group attached to benzene, that carbon that is attached to benzene becomes a carboxyl carbon whenever you use this reagent. Okay? Okay, a couple more reactions, then we could go. Supposing I give you this. This reaction we call Friedel-Crafts acylation. Friedel-Crafts acylation, anytime you have carbonyl group attached to alkyl group, and that carbonyl group is attached to a chlorine atom, and then you use aluminum chloride as a catalyst. This is what you get. You get electrophilic. That's what you get. Now, the beauty of this reaction is we could convert the carbonyl group to a methylene group by taking hydrogen and some catalyst okay. This reagent here will transform a carbonyl group that is attached to benzene into a methylene group right here. This reagent, okay, hydrogen over some catalyst, either palladium or platinum, will transform the carbonyl group that is attached to benzene into a methylene group, which is this one here. Okay, now supposing I give you this. Yes.
Does that have to be a methyl group, or could it be a different R group?
Yes, it could be an R group. Yes, it could be. That's a general reaction. Very good. And the question that Emma asked, does this have to be a methyl group? No, it could be any alkyl group. Yeah, Tikia, you have a question? This is an alkyl group. This is a CH2 and a CH3. Okay. Okay, supposing I have this. Okay, if I do this, hydrogen and some catalyst, this reagent here will transform the nitro group to an amino group. At the same time, it will also transform the carbonyl group to a CH2. So this is what you're going to get. So this becomes a CH2. However, if all I want to do is just to transform the nitro group, and I do not want to change the carbonic group, then I will do this. Hydronium ion or hydrogen chloride over ion. Any ion, or sometimes tin can even do it. So now you get this reagent here will transform the nitro group to an amino group, but it will not change the carbonic group. So you begin to see some of the things that we could do with these chemical reactions. So when we come back on Thursday, there will be a quiz, a pre-exam quiz on Thursday, and then we'll finish up by working problems on Thursday. Right now we have essentially finished chapter 16, and so tomorrow, when we meet tomorrow, we are going to be discussing chapter 16. Yes, there. Huh? Chapter 16? Yes. Oh, there is no name to it. It's just a reduction. No. That's it. Over there. Yeah.